Any other questions about the midterm? Okay, good. Okay, what I would like to talk about now is get back to our NP completeness world again. And let me see if I can do this. Bang. Hold on, I thought I had done that. Boom. And last class, we started talking about introducing this idea of NP completeness. And I believe this was the problem of the day. Can everybody confirm that this is the problem of the day? The problem of the day was, suppose someone sells you, okay, a magic subroutine that can solve the traveling salesman decision problem in order and time. You've got a graph G. G is, has n vertices and m edges. And suppose someone says, hey, Mac, you want to buy a subroutine that can solve traveling salesman in order n plus m time. Okay, the decision problem. Okay? If you bought one of those, now, could you use this? This is only a decision problem. This will take the graph G and a bound K, okay? So TS, traveling salesman, TS, traveling salesperson, decision problem, okay, is going to return true if there is a tour of cost less than K, and false if there is a tour of cost less than or equal to K. Let's make it less than or equal, let's make it like that. Okay? So if there is a good tour, a tour of weight K, your thing is going to say yes, and if there is no tour of weight K, your thing is going to say no. Now, how would you use that subroutine to reconstruct the actual traveling salesman tour? Now I give you a graph G. I want to find the TSP in that graph. How do I find it using this yes-no thing? Can anybody use the yes-no thing to reconstruct the actual tour? Okay. If you can't, the yes-no thing, the traveling salesman decision problem isn't that useful, right? If I prove that it's hard, but I can't reconstruct the traveling salesman problem tour from it, it's probably not so relevant, right? But can I use that yes-no question to tell me what the tour is? Someone have a way to do it? How would you do it? Okay, so you want to say, what I could do is say, certainly the weight of a TSP tour is going to be somewhere between 0 and the sum of the weight of all edges, right? And if I then call the TSPD, on G with a particular query weight of Q. Q originally is in the midpoint of this. Then whether it's bigger or smaller than that, I can believe that by doing binary search in the log of this many queries, I could find the cost of the tour, right? That everybody should believe. Does everybody agree that you could use the yes-no question to find the cost of the optimal tour? Right? If you get to the point where this subroutine says, yes, there is a tour of size Q, but when you call it with GSPD of Q minus 1, there is not a tour, you know that the shortest possible tour is going to be that. Right? So do I believe I can use the yes-no thing to get the cost of the optimal tour? That, I think, should be obvious to everyone. Do people agree with that? But I want the tour itself. Can I find the actual tour using this yes-no thing? Is there a way I could use the yes-no? Now that I know that the tour is the minimum cost tour is 96, is there a way I could actually find what that tour is? Yeah? You're saying I could look at all the edges and try to see if they're adding up to 93, and this sounds hard. Can I use my magic subroutine to do something? You're not using your subroutine, yeah? What if I remove edges from the graph? What if I have a world where I have an optimal TSP tour, there is an optimal TSP tour, and let's get rid of this thing, and there's other edges in this graph, right? What could I do? Once I know that this TSP tour is of size Q, what if I take my graph, G? Sorry about this. This is probably hopeless. Take G minus an edge xy. And I ask again, if I delete an edge and I ask whether there's a TSP tour of size Q, one of two things is going to happen. Okay? Either it's going to come back with a yes or a no. Right? What if I delete the edge and the tour is still a tour of size Q? What should I do? The edge is gone. Why don't I now work on the smaller graph? I didn't need that edge in my optimal tour, right? What if I go through every edge? If the weight was if there is still a tour of that size after I delete it, okay, I might as well delete it, right? What if, when I delete it, the answer now comes back no? There's now not a tour anymore when I do that. What should I do? What? I should put that edge back and continue continue querying and try to delete other edges, right? That means that edge probably is presumably is on the optimal tour, or at least an optimal tour. Actually, I guess if you delete it and it breaks it, that I guess means that edge is on all optimal tours. Okay? So maybe I'd remember it, but I'll remember that edge is going to be a special edge, right? But that's not so important. I'm going to put it back in the graph and now try to delete everything else. My claim is but after I do this deletion process, the only things that will remain is going to be the edges I want. Okay? Any questions about that? So the interesting thing is, how many queries am I making now? If I have a graph on n vertices and m edges, how many queries am I making? I'm making at most m queries. I'm making exactly m queries on this phase, right? And so if you could find solve the decision problem in order n time, and if I'm going to be able to solve this by making m such queries, well, that would give me an n times m algorithm, okay? But that depends on me getting a magic linear time oracle that's capable of solving this problem. If I could solve the decision problem fast, I could solve the optimization problem fast. But if I can prove that this decision problem is NP complete, then what do I know? There's no way that I can solve the optimization problem fast. Okay? Any questions about that? Okay, let's go and review the big ideas of NP completeness. Okay, and make sure we really get that story. sorry about this, too much pollution on there. What am I now going to ask you? This is the main idea of NP completeness, the big and only idea with NP completeness. Suppose I have an algorithm to solve the Bandersnatch problem. And that Bandersnatch is an algorithm. Bandersnatch is a decision problem. So Bandersnatch returns yes or no on whatever its input is. True or false, yes or no, that's what it is. And how does the Bandersnatch problem get its answer? In this algorithm, we translate, the input of the Bandersnatch problem to the input of Bobilli, which is also a yes-no problem, in such a way that when Bobilli on the translated input instance is true, Bandersnatch of G is true. And when Bobilli of Y is false, Bandersnatch of G is false. If we did that translation such that the answer to Bobilli of Y is the same as the answer to Bandersnatch of G, well, then we can report Bobilli of Y as the answer to Bandersnatch of G, and we've got a correct algorithm. Okay? So if we do that, this is clearly a correct algorithm. For if we can make this translation work, we have a correct algorithm to solve the Bandersnatch problem by translating it into Bobilli. What are the any questions about that? What are the implications of this? The implications of this are, where do I go here? Hold it. If my translation is fast, meaning it runs in polynomial time, then a fast Bobilli solver will give me a fast Bandersnatch solver, where I'm going to pay the time of doing the translation and then the time of calling Bobilli on the translated input. Okay? So if Bobilli is fast, if I have a fast way, if translation is fast and Bobilli is fast, I get a fast algorithm for Bandersnatch. But if I know that there is no fast algorithm for Bandersnatch, if I know that Bandersnatch is a hard problem, if I know that there is no way you can compute it faster than P prime n, then P prime n minus the cost of translation, okay, must be, okay, the, a lower bound on computing Bobilli. Because if there is no fast way to compute Bandersnatch, and I just showed you a fast way to compute Bandersnatch if Bobilli was fast, this is an argument. If I know that Bandersnatch is hard, and I show you how to compute Bandersnatch quickly if Bobilli ran quickly, if there's no way to solve Bandersnatch hard, that means that there is no way to solve Bobilli quickly. And so Bobilli is just as hard as Bandersnatch. Any questions about that reasoning? That is the key reasoning of what we're going to be doing for the rest of the semester. Okay? If we have a problem that we know is hard, okay, and we show that we could solve it quickly, if there was a fast algorithm for some other problem, then that means there can't be a fast algorithm for that other problem. That is the reasoning that we are using. Any questions about this? How many people get this reasoning? Okay? Any questions about it? This is a very clever idea. if you have a problem that you can absolutely guarantee prove is hard, okay, where you know that there's no fast way to do it, fortunately we have such a problem. What is that problem? Talked about it last time, but it's a problem called satisfiability. If I show you that my satisfiability, I can argue for many reasons, is a hard problem, okay? And if you could show me that you could solve satisfiability using a, a problem like traveling salesman. Oh, if we could compute traveling salesman quickly, we could compute satisfiability quickly. What does that mean? Well, that means you can't compute traveling salesman quickly, because there's no way to compute traveling satisfiability quickly. If you could use traveling salesman to compute satisfiability quickly, the world would collapse. So that means that there is no fast way to compute traveling salesman. That's the reasoning we're doing. Any questions? Okay. Let's now look at more specifics. So I talked about satisfiability last class. Let's just remind ourselves what satisfiability is. Satisfiability is, I am giving you a logic problem where we have I think it's in CNF form if you're an expert on logic. But basically we've got clauses which are ors, V1, or not V2, and not V1 or V2. Do you see how I translated this representation into a logic formula? This is supposed to be just this is how I like to write it. This is how you like to read it. Okay? And what is the question? It's a question on these logic formulas. Is there a way to assign the variables, true or false to the variables, such that you can make this thing true? Okay? There are, if you've got n Boolean variables in your formula, here n is equal to 2, but in general, if you have a formula on n variables, there are 2 to the n possible ways of assigning values to the variables. If you try all of those 2 to the n possibilities, and one of them comes up with the formula being true, we say that that formula was satisfiable. Just gave you an easy algorithm for this. The trouble is it was an exponential time algorithm because it went through all 2 to the n different logic assignments. Okay? Satisfiability, given a formula, is there a way to make it true, is the mother of all hard problems. Okay? There is no known fast algorithm for it. Okay? If you talk to Professor Mitchell and say, give me a fast algorithm for solving satisfiability, he will hang his head in shame. He will say, I can't do it. Okay? I am not strong enough. Okay? There is no algorithm person in the world who knows how to solve satisfiability quickly. And there is a lot of other reasons why to believe that it can't be solved quickly. Okay, satisfiability is the mother of all hard problems. Any questions? Any questions about satisfiability? Okay, I went over this last time. Now, once we have a hard problem, we can start to look at other problems. okay, and try to prove whether or not they are as hard as satisfiability. The first one we're going to do may be a little letdown for you, because it's going to be a flavor of satisfiability. Now, 3 satisfiability is this problem of satisfiability where every one of my clauses has exactly 3 literals in it. Okay? Does everybody agree that each one of these clauses is this ORed with this, this ORed with that? In 3 sat, every clause has exactly 3 literals in it. Okay? So in some sense, it's a simpler version of satisfiability. Remember, full satisfiability, the clauses could have any number of variables in it, right? Let's look at an even more simple version of satisfiability. Suppose we consider the 1 satisfiability problem. What is the 1 satisfiability problem? I am going to be giving you a bunch of subsets of literals, each of which has only 1 literal in it. People see what I've got now? I've got clauses made where each clause has only 1 literal in it. Right? 1 Boolean variable that's either negated or not. This would be written as what? This would be written as not V1 or V2. Actually, sorry, let me write that again. Or V2 or not V2 or V3. Is there a way to make this formula true? Does everybody see what I've got here? I've got a very simple satisfiability problem. Okay? Every clause has 1 literal in it. If every clause has 1 literal in it, is there a way to tell whether or not it's satisfiable? If you ask Joe Mitchell, he could do this one. Okay? How would you tell if a clause is satisfiable if it's like this? Yeah?
Go through each clause and then update the truth value accordingly, and then if there's a contradiction, then it's possible.
What kind of updates do I have to do? Not V2, V1. What does this tell me about what V1 has to be if I'm going to have any chance to satisfy it? V1 had better be equal to false, or else I have no chance of satisfying this. Does everybody agree? Actually, take it back. You shouldn't agree because I wrote this wrong. What if the outer thing is an and? Now do you agree? Now I have to satisfy the first thing. So V1 had better be false. What did I have to satisfy this one. How can I do it? V2 is equal to true. And I have to satisfy this one. What do I got to do? V2 is false. Is that a problem for me? That's a big problem for me. I can't do it, right? I have a contradiction. So long as 2 of the clauses, I don't have, if I have single element clauses, so long as I don't have one clause with a variable and another with its negation, there is going to be a way to make it true. Okay? But if there is, then I'm stuck. Does everybody kind of see that? Any questions about that? So the one satisfiability problem, if the clauses are so simple that every clause has one literal in it, this is easy. Maybe satisfiability is easy for slightly larger clauses. Okay? Maybe clauses of size 3 are small enough that, deciding whether or not it was easy or hard, whether or not there was a way to satisfy it, was simple or not. Okay? I don't know. How would we prove that satisfiability is as hard as regular satisfiability? One satisfiability obviously is easy. Sorry about this. How would I argue that 3 satisfiability is hard? Okay? What would I have to do to prove that 3 satisfiability is hard? I've got to go back to my Bandersnatch and Bobilly thing, right? Where do I got it? Here. How would I go and prove that 3 satisfiability is hard? What is Bandersnatch and what is Bobilly? What problem is Bandersnatch? What? Satisfiability. And what is Bobilly going to be? What is Bobilly going to be if I want to prove that 3 sat is hard? What is Bobilly? If I could find a way to translate an arbitrary set of clauses into clauses that are of size 3, okay, such that the translated version is satisfiable if and only if the original problem is satisfiable, then I will have proven that 3 sat is hard. Because if there was a fast way to solve 3 sat, I will have a fast way to solve satisfiability, and there is no fast way to solve satisfiability. Any question about my strategy? Okay? Yes?
So we can assume that satisfiability would be hard, right?
What?
We can assume that satisfiability would be hard.
You can assume that satisfiability is hard. You can assume that because I tell you. And because every algorithm's and I will tell you that because every algorithm's person in the world knows that that is the hardest problem. You solve that one, you are the king of the jungle. Okay, you're famous. Okay? Joe Mitchell in his idle dreams has thought about it. He's played with this thing and given up. Okay? So has every other algorithm's person in the world. Okay? And there are other reasons, which I'll talk about later, that are even stronger than that. Okay? Any questions about that? Okay? So now I've got to show you how can I translate a general satisfiability problem into a 3 satisfiability problem. Okay? Let's look at this translation. I'm going to do this translation from sat to 3 sat, 1 clause at a time. Okay? How can I take a clause in sat on 1 literal? Okay? How can I make it into a set of clauses on 3 literals such that if this is satisfied, all of these are satisfied? What I'm going to do is I'm going to turn this one clause into 4 3-element clauses. I'm going to make up 2 new variables. I'm going to call them V1 and V2, if that's to be catchy. And my 4 clauses are going to be, one element is going to be this Z1 in all of them, and it's going to be all 4 possible patterns of negated and not negated. Notice that these 2 are not negated. These 2 are negated. This one is, the second one is negated here and the first one isn't. The first one is negated here and the second one is negated here. Does everybody see that these are 4 different 3-element clauses? Now, why did I do that? My claim is there is one way and only one way to satisfy all of these clauses. What is the best way to satisfy all of these clauses? If I want all of those clauses to have at least one true literal in it, what is a truth assignment that will do it? Okay? What way can I make all 4 of these have a true literal? Yeah? If I set Z1 to be true, does everybody see if I get Z1 to be true? True, 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 true. All of these clauses are satisfied. Do you agree? So if this 1-element clause was satisfied, these 4 3-element clauses would be satisfied. Is there any other way to make it satisfied? If Z1 is false, these things go away. Is there any way I can assign values to V1 and V2 to make all 4 of these things true? He's shaking his head, no. What do you mean? Why don't I can make this thing be true if you want? That satisfies this one, right? Oh, but now you're telling me, wait, this is false. Well, I still have V2 at my disposal, right? I can put that one to be true. But what happens? Now I'm out of luck. Did you see that? By setting my V's and V2s, I can make 3 of these things true. But I can't make all 4 of them true. Right? This clause, these 4 clauses on 3 variables are logically equivalent to that 1 clause on 1 variable. Does everybody agree with that? Okay, I'm trying to do a translation. That's all I'm trying to do. What about the next one? If k is equal to 2, meaning my clause has 2 variables, z1 and z2, how can I make clauses of size 3 with the property that these will be satisfied, the set of them will be satisfied if and only if the original one was satisfied? If I only add 1 new variable, v1 and v2, and v1 prime, now what do I know? If either z1 or z2 is true, both of these 2 clauses are satisfied. But if both z1 and z2 are false, then there is no way I can save it with my 3rd extra variable. Does everybody agree with that? These clauses are logically equivalent to those clauses. Okay? Any question? If my set problem had this clause, z1, z2, z3 on 3 elements, how would I convert it to a set of 3 element clauses that are logically the same? Just copy it again, right? It's a three-element clause that is logically the same. So what's the hard part? What if I am given a big clause? See, I've got this big clause on 6 variables. How can I turn it into 3-element clauses that mean the same thing? Does everybody have an idea? Anyone have an idea of how I could turn that 6-element clause into 3-element clauses that mean the same thing? Okay. What if I did this? Let me make it a different color. What if I just broke it in the middle? Look, Ma, they're 3-element clauses. Okay? Do these 2 clauses mean the same thing as the red thing? Seeing someone shaking their heads, no. Why is it not to mean the same thing? What if I had true, false, 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 false? What's going to happen here? This clause will come out to be true, and this clause will come out to be false, and so all of them are not satisfied. Does everybody kind of see it? These 2 clauses are not the same thing as what Z is. Okay? Any questions? But let me show you a way that you can make something that's logically the same as this one. What if I did Z1, Z2, V1, and not V1, Z3, V2? And what if I did not V2, Z4, and V3? And what if I did not V3? Uh-oh, go away. Uh-oh. What if I did this? Does everybody see how I have now broken that 6-element clause into 4 3-element clauses? I've got my original 6 variables here. I've got them arranged in a chain. V1, not V1. V2, not V2. V3, not V3. See how I got that? What's interesting about this? If there was a way to make it true, in this case, let's look at the example that you had before, where there was only one example that was true. Let's change it just to make it a little bit more exciting. I'm going to make this to be false here, but true there. Does everybody agree it's the same problem that he had before? There's only one true literal? What's going to happen? If I do it with this, what do I know? Z1 is going to be false. This is going to be false. How would I save the day? What do I know that V1 has to be? What does V1 have to be to save that clause? True. Now, this one's going to be false. and Z3 is going to be false. What do I need in order to save the day from V2? True. That makes the not thing false, right? Fortunately, now I get a true literal. Does everybody see that? And now, what should I do with V3 in order to maximize my chances of satisfying everything? I don't need V1 to V3 to be true. If I make it false, I get a true in the next clause, regardless of what those things are. Do you see what's kind of happened? This is kind of a cool thing. I have translated this big old clause into a set of little clauses. And the only way to get all of those clauses satisfied is if the original clause was satisfied. Does everybody kind of see that? What happens if none of them were true? What am I going to do? False, false, true. I'll save it. That makes that false. That makes that false. This I'll make true to save it. False. Let's say that this time this was false. The only thing I could do was make that true to save it. And now I'm out of luck. Does everybody see that if I didn't have any true literal in the original expression, I can't save all those clauses. If I have at least one, I can save all those clauses. So this set of clauses on three-element things is equal to this clause. Okay? And by constructing that chain, I have shown you how to translate any clause of any size into a set of equivalent three-element clauses, right? So I have a three-set problem now that if you could solve it quickly, if you could solve it, it would tell you the answer of the original satisfiability problem. If you could solve three-set quickly, you could take any satisfiability problem, use this translation to create clauses of size 3, and then solve it quickly. And that would tell you yes or no, was the original problem satisfied? But what do we know about satisfiability? There is no way to solve it quickly. The translation is right. The translation is fast. If the input was of size n, maybe it's going to create something of size, I don't know, something like 3 times n or 4 times n in size. It's not that much bigger. But if you could solve 3-set quickly, you would solve set. You can't solve 3-set quickly, so this is a proof that you can't solve 3-set quickly. Any questions about that? Do people see how that reduction goes? Any questions about that? Okay. Now let's think about this for a little bit more. Okay? What do I like about it? So I've now shown you what? Let's go through my slides just to say it. Why does the chain work? I went through that kind of an argument. Basically, what I've shown you is the important thing was this. Any SAT solution will satisfy the 3-set instance I created, and any 3-set solution to my 3-set problem will tell you how to set the variables in your original SAT problem. You did this translation. You knew what were V's variables that we added and what were Z variables. If you solved the 3-set problem, you could go back and tell him the answer to the set problem. Okay? Thus the two problems are equivalent. And if set is hard, okay, 3 set must be hard. 3 set is every bit as hard as satisfiability. Any questions? Okay, let's look at some other generalization of this. That's interesting. Sorry, I'm having problems here. Is the 4 set problem hard? Okay? Suppose I asked you about 4 satisfiability. Given a set of clauses where every clause has 4 variables, is that as hard as satisfiability? How would I prove the 4 set problem was hard? Okay? Let's go back to my reduction. What would I have to change? Okay? Sorry about this. If I have a set of a clause of 1 variable, okay, how would I create an equivalent set of 4-element clauses? How many clauses would I need and how many variables? If I want each one of my translated clauses to have 4, how would I go ahead and do that? Can anybody, yeah? Now if I want to do 4, I'm going to make this to be 3. And I'm going to create, what is it, 8 new 4 variable things. Is that right? I'm still going to keep the payload of it. But now I'm going to have all 8 different patterns of 3 of these dummy variables. Right? Do you see how I can generalize this idea to 4 clauses, clauses of size 4 fairly easily? Okay? Any questions about it? The same kind of translation would work. What if I want to translate, by the way, a 3 set clause? Remember I told you 3 set was every bit as hard as regular set? In this reduction, I'm translating clauses of size 1, of size 2, of size 3, 4, 5, dot, dot, dot. Maybe it's easier if I start from 3 set. How would I translate a clause Z1, Z2, Z3 into 4-element clauses that mean the same thing? 3 set is nice and simple. Every clause has 3 elements instead of translating all the complicated sets. How would I translate a 3 set clause into 4-element clauses? What would I do? Can anyone propose me a translation? How many variables do I need to add? How many clauses do I need to add? How would I translate a 3-element clause into 4-element clauses? Okay, such that they're logically the same. Does anyone have an idea? Yeah? Z1, Z2, Z3, V1. Does everybody see by making 2 clauses with 1 new variable? Okay? Do you see how I could convert it into a 3 set problem, which is hard, into a 4 set problem? If 3 set is hard, this means that 4 set is hard. Okay? And see how that translation was easier because I knew all the clauses had 3 elements than the original one we did. That's why we're going to like 3 set. Because 3 set is a kind of easier thing to work with. It's hard. Every bit as hard as satisfiability. But it's nice. Everything has exactly 3 clauses, elements in each clause. Any questions? Now, could we prove that 2 set is hard? Any questions so far? Could we prove that 2 element clauses, if I just give you, okay, if you're allowed to use only clauses of size 2, okay, is there a way we can convert 3 element clauses into clauses of size 2? Okay? If there was a way we could convert them into a bunch of clauses that were equivalent of size 2, that would mean 2 set was hard, right? Can we? Well, I think we're going to run into trouble. Let's look at our original reduction. Where do we run into trouble with our original reduction? Hold on, I don't know, something weird has happened. Do you see that on this latter thing, the last part of our reduction, we would get into trouble with a chain idea? Remember, we had this idea where for the big clauses, we were going to break them into smaller clauses by using the chain? Notice that we would get into trouble with 2 element clauses, right? We had not VI, Z something, and VI plus 1. If we only have 2 element clauses, okay, we can build chains that contain nothing. That won't help us. Or we can't build chains. In fact, this idea works for 4 set, 5 set, 6 set. It doesn't work for 2 set. You know why we can't prove that 2 set is as hard as 3 set? Can anyone come up with an idea why we can't prove that 2 set is as hard as 3 set? It's because 2 set isn't hard. There's a polynomial, there is a fast algorithm for 2 set, it turns out. It requires more cleverness than I want to talk about here. 1 set is easy, 2 set is easy, 3 set and beyond is hard, okay? And by doing these reductions, we're able to prove that that satisfiability with only 2 element clauses is every bit as hard as anything else, any other satisfiability. So before we only knew that satisfiability was a hard problem, now we know that satisfiability and 3 satisfiability are both hard problems. Any questions? This by itself may not excite you. You never cared about satisfiability before you came into this class. You never cared about 3 set. But starting next class, okay, I am going to show you problems that you do care about, that you've heard of in other contexts, that we've looked at in this algorithms class, are every bit as hard as 3 set, okay? And we're going to use that as our new mother of all hard problems. Any questions about what we've done in here? Okay? If not, have a good Thanksgiving. Think about hard problems, okay? And we will talk about it again right after Thanksgiving. Okay, thank you very much.